Okay, hello everybody, welcome. So today we have an MSc seminar by Ohad. So briefly about Ohad. So Ohad holds a BSc from Electrical Engineering Department at the Technion since 2014, and he has been pursuing his master's degree at TASP since 2015. Right, go ahead, Ohad.
Thanks, Vadim. Hi, guys. I would like to talk to you about the issue of my master's degree. My research dealt with hypothesis disambiguation and retrospective for robust perception in an ambiguous environment. In general, in the modern world, autonomous navigation is a key aspect, both by the research community as well as on our day-to-day regular routines. For instance, autonomous cars is a developed field, both in the research community and in large companies such as Google, NVIDIA, etc. As well, we can see autonomous navigation in our indoor and outdoor products that work on mapping the current surrounding as well as doing localization at the same time, SLAM. We can see this either by quadcopters and by indoor products such as the Xiaomi Roborock, for instance. If we look at the autonomous navigation high-level framework, we can actually divide this framework into four main sections. The first section will be to estimate the current location, where in the beginning, we have an initial estimation, which is called the prior estimation. The second section will be to execute an action. In general, in the planning phase, which is outside of the scope of this work, we wish to choose the best action, where best action is a very wide term. But again, this is outside the scope of this work. After we choose an action, we commence this action, and after that we receive an inference by retrieving a measurement that is resulted from the surroundings we are currently located at. After that, we do another estimation of our location and our surrounding in the inference phase, which is the SLAM. This work actually deals with an ambiguous setting where the retrieved measurement can be correlated to a number of landmarks in our surrounding. For instance, matching corridors, as we can see here on the upper left image, or similar chairs, tables, etc. Now, how can a certain scenario be ambiguous? The first, as mentioned in the previous slide, it can be due to a very high list setting, such as a setting which has large identical chairs and tables, etc. Second option would be a limited imperfect sensing, where actually a sensor can't retrieve or view all the possible landmarks in our surroundings. Now, how can we deal with such ambiguity on inference and planning? And in general, how can we make our perception more robust in such a case? Now, in general, in most researches, we have the data association assumption. What does that mean? Given if we have two identical landmarks, commonly it is assumed that if we retrieve the measurement, the inference phase, we can perform the correct association, meaning the landmark, the observation Z can be associated to the right landmark L1 or L2, for instance. And what actually can occur if this if this data association is false? Well, on the minor case, what can happen is that our trajectory would become suboptimal, and our estimation would be fixed as we proceed in our route. On the worst case scenario, this can result in a dead end to our robot's trajectory and to a location where we cannot assist to the robot anymore. Now, this is a simple setting actually to show the motivation for my approach. Consider a setting where we have two identical mugs and two identical tables, which are located in a serial order, one after another. Our robot takes its first action from an initial location where we see the red circle is actually the prior estimation marked in red. At time k minus 1, the robot retrieves a measurement of a single coffee mug, but he can't make the correct data association to which one of these two measurements, to which one of these two coffee mugs the measurement belongs to. Therefore, a single hypothesis now divides into two hypotheses that live in parallel, one for each coffee mug. We're currently now, according to the gathered information we have so far, we can't distinguish which one of these coffee mugs has the correct data association. Time k minus 1 again, the robot takes another action for it. Now at time k, the robot gets a measurement of a single table, but again, he can't do the correct correlation knowing which one of these two tables is the correct one. Therefore, each of the two hypotheses split again into two hypotheses. So in general, our full belief is built from four hypotheses which live in parallel to one another. The question we are trying to address actually is here: does this gathered information we obtained at time k can have any effect on our ability to distinguish between the two hypotheses we had at time k minus 1? Can this make our perception at that time more robust than it is? A bit about related work that actually dealt with relaxing the data association assumption. Indelman at CSM 2016 actually performed inference from arbitrary poses and addressed the data association relaxation by using multiple robot collaboration. Potzel and Sunderleft shows how multiple data association can be described by using a switchable constraint in factographs. Fourier addressed this in the direction of an incremental solution to address the exponential growth of the GMM of the belief of the number of hypotheses as we go along the trajectory. They address this by updating the relevant nodes, which needs to be updated in a base tree. We should mention, though, that he assumed the probability of each one of the hypotheses to be the correct one to be identical. Patak was one of the first to address this in the planning phase and took the aspect of relaxing the data association to planning. And he also assumed different probabilities to the hypothesis to be the correct one. Tuchayev at IRIS 2019 addressed the aspect of relaxing the data association and the aspect of classification. He did this in order to develop a view-dependent classifier model. But we should mention that all of these works mentioned, as far as we know, none of the works we know of today dealt with the aspect of understanding how current information can have any impact on a past hypothesis and a past time. As far as we know, we're the first to show this. So in general, our work deals with exactly this issue. In fact, we select or receive an I hypothesis from a past time from some time k minus p, which is some strategic point or a reevaluation point. And we want to examine how does the obtained information we have till time k has any effect on our past hypothesis weight, which weight by weight I actually mean the probability of this hypothesis to be the correct hypothesis in a way. So what we will show? We will show an incremental form where we, in addition, we will show an incremental form where we perform reuse of previous step calculations in our current step calculations, and by that we actually will be able to reduce the complexity of the calculations by an order of 1 magnitude. In addition, we will show how this ability allows us to perform a more generic form of pruning, and also to reevaluate the probability of a specific DA. I should mention that this work was written in a paper called Hypothesis Disaggregation Retrospective. It was this paper was published also in the Letters and will be shown in ICRA, the International Conference of Robotics and Automation, in May 2022. So a bit about the notations. So B of xk is actually the belief at time k, which is the probability of our state given history. Our state is actually a vector built by all the Roberts poses from the initial location, which is x0 till till xk. And hk, which is a history, is actually built from two sets of vectors. The first vector is actually the set of actions we have till current time. And the measurement is actually a vector of all the obtained measurements from current time, from the initial location till current time. B of I xk, in the case dA is not resolved, we note that I hypothesis at time k, which is what is mentioned actually here, where gamma is actually a vector of data associations. Each data association is mentioned by beta, and each data association can be actually associated to a specific landmark in our surrounding from the total of L landmarks we have. And the BI and the belief minus is actually only to notate the propagated belief. Which propagated belief, I mean, is only without the last obtained measurement. A bit about the assumptions in our work. The first assumption we have is actually that the map is given. We know the location of the landmarks, and not only that they are known, they're also static. Assumption is actually the observation and Marshall model we use, which are the standard ones, where we use standard Gaussian noise for both the observation and the measurements. So GMM belief. Sorry. So when we remove the D assumption, we need to marginalize actually over all the possible associations. So after we do marginalization over all associations and commence chain rule, the belief actually divides into two main sections. First section would be the right section here would actually be the I belief, which is a single hypothesis, which lives in parallel to a set of MK hypothesis. The second section would be the weight, which is noted here on the left side, which is actually the probability of this hypothesis to be the correct one. We note this as the weight of the hypothesis. So let's try to formulate actually what we're trying to solve. So given we have a belief, a time k minus p, we wish to update that belief given the current information, which actually means we take its weight, the weight as it was mentioned in the previous slides, and when we want to review how this value is updated given all the history we gave it till time k. In the simple case, which is the first section, we would like to review how does this take place on a single step update, where we actually have an hypothesis at time k minus 1, we wish to evaluate given the information till time k. And a little of the mathematics, we actually see that by extracting the measurement and performing base rule, we retrieve the following multiplication. We get actually the original weight, which we wish to evaluate, multiplied by a factor which we note as the update factor. In order to calculate the update factor, the initial part, we would like to do the calculation to denominator. How do we do that? We need to do a marginalization on all possible landmarks, and the robot poses at current time, which we see actually here. After we commence chain rule and marginalization, after we commence chain rule, we retrieve these three arguments. The first argument is an argument which we know is the observation model, standard one. Second one is this one, which is actually the probability of the J landmark to be viewed from the current robot's pose, which actually sheds the finite borders to this integral. And the third section will be actually the propagated belief, which is noted here at C. Since this integral has finite borders, in order to calculate it, we use sampling. So what we do is we sample the current robot's pose using S samples from that. And by that, we retrieve this argument over here. In order to avoid the calculation of the denominator, what we like to do is actually we define a weight tilde, which is the multiplication of the value of this argument multiplied by our original weight. And what we actually do is we do the calculation of all weights at the reevaluation point, And after that, all that's left to do is only normalization of that weight again, which is noted here. Now let's try to take this solution to a more generic form. Let's try to select it for any valid value of P, for any valid P steps. So again, by commencing in a serial fashion, extracting the current measurement and commencing base rule in a serial fashion, what we see is actually, we again retrieve the original measurement which we want to evaluate, multiplied by psi of mk, which is again the update factor, and which we see in the denominator is actually a multiplication of many arguments. Now, in the naive form, if one would like to make a calculation of each one of these arguments, you will need to commence it needs to commence this calculation for each argument from scratch. We show in our approach actually a more adaptive approach, which can commence reuse of previous arguments calculations, which we'll now show. So if we take a given argument from the denominator again, which we wish to calculate, by commencing again chain rule over the robot's pose at time n plus j and all possible viewed landmarks, we retrieve the following argument, which is again, as we've seen for a single step update, the standard observation model multiplied by this argument. In our work and the full, which in the thesis as well as in the article, where the full calculation is shown, we actually prove that this argument over here, b of I minus m, is actually a GMM component built from S components, which the interesting part about this argument is actually that it's built from the predefined samples from the previous step of m plus j minus 1. Where zeta, noted here, is actually the weight of the GMM and hypothesis, and the hypotheses are given actually by the motion model for each sample from the previous step. This f function noted here is actually a summation of the probability of a measurement from previous step to be correlated for each one of the landmarks in our settings, given a specific sample of the robot state at past time. Again, we should note that since our approach is incremental, these calculations were taken from the previous steps and now reused the time n plus j. And the naive form again would have obtained a new set of samples and do the recalculation of the defined GMM marked here in green in the previous slide. So again, if we wish to do the calculation of the argument for m plus j in the same fashion mentioned for a single step, since we have finite borders, we need to do a set of samples of the GMM belief, of the belief of b of I m plus j. So we sample again a set of S samples, and eventually our calculations summarize into this. Now, as mentioned, for the next step again, we would reuse these calculations for again and predefine a GMM belief. So now that we have seen how does the calculation for a single argument for m plus j does, we need to do the calculation for all arguments in our update factor. And again, as mentioned, for a single step in the same fashion, in order to avoid the nominator calculations, we define W tilde weight, and we do this calculation for all the hypotheses at the reevaluation point. And what is left for us to do now is only normalization and scaling, which is shown here. So a bit about complexity calculations. So when we actually do the complexity calculations in the naive approach, we see the complexity is contained on the square number of the steps from our reevaluation point. By doing the calculation as in the reuse in the incremental approach, as we suggest in this work, we can reduce the complexity in one order of magnitude of P. Notice actually that in both approaches, the S, which is the number of samples, affect in the same fashion. We now wish to show two additional aspects that can be affected by the weight reevaluation. The first aspect is actually the probability of a specific DA. in a given time point. In general, a specific DA of a given landmark index C, which is noted here, can be shown in the following order. If we observe again the gamma indicator, which was noted in the past, we can divide it actually into two sections. First is the left section, which is a vector of all the DAs till time k minus p, and the right section is actually the last data association that we commence at time k minus p. In the GMM, at time k minus p, for instance, we have several hypotheses with different vectors of DA. Each one has a different gamma indicator, but some of them can have the same data association at time k minus p at the last point. For instance, in this example here, what we see, we have four hypotheses which live at time k equals 2, but the green and the orange hypothesis are both generated from the same data association, which is landmark L3. Therefore, we suggest actually that the probability of this data association to be the correct one would be the summation of these two hypotheses noted here: the green and the orange weight. Therefore, it's actually pretty straightforward that if we were to retrieve more information up to time k equals 3, for instance, in our example, or in general, more information till current time, this information can have an effect on our weight reevaluation. As we see here, this is the weight distribution given the information till time k equals 3. So the probability of this data association to be the correct one would be different. The second aspect that we would like to talk about is actually enhanced pruning. In the regular case, pruning takes place by comparing the current weight with a given threshold. If the weight value is below this threshold, these hypotheses are actually pruned. As we see in the example here on the right, at k equals 1, all hypothesis values are above the given threshold. Therefore, a full spanning tree is created till k equals 3, which we can see here. Yet, one should consider that in case part of the updated weight values are below threshold, this would actually mean that all of the descendants of the pruned hypothesis, as well as all the descendants in current time, and more specifically the descendants in current time, can be pruned as well. If we look again in our example, if we do the reevaluation, the green hypothesis is actually now below threshold, which actually means that all this spanning tree of the GMM can be pruned as well. This has a direct effect on the GMM belief we have at current time, that in the original, we had 8 living hypotheses, which now reduce into 4, as well as a direct effect on their weight distribution due to scaling. Now, a bit about our simulations. A bit about the simulations we did. In our simulations, we have actually done by creating a very alias setting. This alias setting was actually done by a scattered of 8 identical landmarks in our surroundings, which you can see here. The landmarks are marked as red triangles. Actually, the simulation we actually did holds 2 sections. The first section was calculating the GMM till the end of the trajectory. And the second section was performing the reevaluation, which was performing reevaluation of the weight. And the point of reevaluation was always the same, which is a single step forward from our initial location. We actually show in this presentation 2 examples. First example is of the 5-step trajectory. And the second example is of a 10-step trajectory noted here. Well, on the 5 steps, we can actually see that we have several hypotheses, both at the reevaluation point marked here. We have 5 living hypotheses, and at the end point, we actually have 4. By the way, the reason why at the end point we have 4 hypotheses and not more, as a result of the exponential growth due to an ambiguous setting, is resulted due to pruning. If we use merging at this finite point, we actually can reduce the number of hypotheses at the last from 4 hypotheses to 2, as marked here in this figure. If you examine our weight distribution actually at k equals 5, we can see that we have 4 hypotheses, as marked here, where we can actually distinguish between the weights of the hypothesis 1 and 3. Both of these hypotheses have a substantial weight. The plot below shows the weight distribution and the reevaluation point. On the left side, we can see the original weight, which is actually over here. Here again, the purple and the blue hypothesis have solid values. Yet when we perform reuse, yet when we use our approach and perform reevaluation given the information obtained till time k equals 5, we see that the blue hypothesis has a significant higher weight than the rest, and is actually substantial. And we can actually commence full disambiguation at past time. By the way, the blue hypothesis is actually the correct hypothesis with the correct association. We should note that in this example, using the merging in current time, actually we can commence full disambiguation at current time as well. But the added value of this simulation would be on the reevaluation of the strategic point, as noted here. At the 10th steps case, we can actually see the number of hypotheses increases along the trajectory at the reevaluation point, which is here. We have actually 4 living hypotheses. And by the time we retrieve the endpoint, we have 28 living hypotheses in parallel. By commencing again the merging effect, our number of hypotheses reduced from 28 to 4. Now, actually, when we take a look at these 2 figures, we can actually see, first of all, the weight distribution at current time, which is the finite point. Where we can see we have a number of solid hypotheses with a number of solid weights, which mean we can't distinguish which one is the correct one at this point. And also, if we commence merging in this simulation, we can actually see again that hypotheses 2 and 3, for example, have significant values. When we look at the reevaluation point and the original weight distribution, again, we have 2 hypotheses with a significant weight, and we can't commence full disambiguation. But in this scenario, when we do when we use our approach, you can see that again we can commence full disambiguation, and the blue hypothesis has a significant higher value than the rest. Where again at this simulation, the blue hypothesis is actually the correct data association. The next slide actually wants to. In this slide, we actually want to show the runtime statistical analysis. The first plot here actually shows the expected number of samples as a function of the runtime. The used number of samples is a function of the runtime. We can actually see again, and we actually compare 2 approaches. The naive approach, which we noted, which is to perform calculations each one of the arguments from scratch, and the incremental approach, which is the approach that we suggest here, that does calculation reuse. When we compare the samples, the runtime as a function of the samples, we actually see a linear growth to both of these figures. To both of these plots, sorry, but we can actually see that the rate using the naive approach is higher than of the incremental approach that we suggest. If we, another plot shown here to the right is actually the runtime as a function of P. P is actually the distance from current time to our reevaluation point. We can actually see that, as expected from our calculations, by the way, as we've seen in the previous slides, that the naive approach, as the distance from our current location increases, this plot increases in a square rate, where in the incremental approach, as we expected, actually, as further as we go from the current time to our strategic point, the growth is actually in a linear rate, as expected again. This is a bit of the histogram calculations to both of the simulations shown. What we try to show you is actually the updated weighted value giving information at different time points. What it actually is shown is that the uncertainty level, which is the histogram, actually can reduce as we obtain more information. We should note actually that this can occur, but we cannot guarantee in all simulations that it can occur. Next, we wish to show a simple simulation for enhanced pruning, which is an aspect we talked about in the previous slides. Again, as before, in our reevaluation point, which is one step further from our initial location, we can see this is the original weight distribution. You can see we have two living hypotheses, where both of these hypotheses live in parallel and are not pruned. At the endpoint, which is 10 steps ahead, these two hypotheses actually had created full spanning tree, which generated into 14 hypotheses and at current time, where four hypotheses 1 to 4, actually descendants of the original blue hypothesis, and hypothesis 5 to 14 are the descendants of the orange hypothesis. Now, if we look at the updated weight using our approach, we see we have full disambiguation, and the blue hypothesis is actually pruned. So if this hypothesis is actually pruned, this again means that all of the spanning tree of this hypothesis marked here on this figure can actually be reduced as well. And more specifically, that descendants in current time can be removed as well, can be pruned as well. So our current time hypothesis, our current time belief actually reduces from 14 components into 10 components, which are components 5 to 14, the descendants of the orange hypothesis. So a bit about conclusions. So we actually shown in our approach that new information can have an impact on the weight distribution, and it can have an impact on our ability to disambiguate between past hypotheses and ability. We have seen that given the information we have in our strategic point was not given to us. We showed an incremental approach. Our work shows an incremental approach to the calculations, where we commence reuse of calculations from previous steps. And at the end, we also saw different aspects that are affected, which is the probability of specific DA and shown in simulation as well, the enhanced pruning ability. Possible future work that this can be taken. Again, our simulation was actually a proof of concept. It was done using a GTSM and MATLAB. We think it would be very interesting to show how this approach can be taken into real-world setting and see how the aspects of the runtime and performance can actually would be affected by taking this into the real world. As mentioned in our assumptions, the landmarks are static and known. We think that it would be very interesting to show how adding a level of uncertainty to the landmarks would contribute to the calculations and the complexity of the approach. This can be done, by the way, in a very simple form, we think, at least. Third thing we think that can be interesting is to review it by taking two hypotheses either given to us or chosen from different time points and review the correlation between them. And if they're correlated, what point of interest can that be taken? And last, which is pretty demanded, you could say in a way, is to take this into the planning phase, which is decision making under uncertainty. We think that this approach can actually contribute, and not only in creating a more robust perception. And we think that it can also assist in our decision making of the current action we are trying to take. Thank you for listening. At last, I would like to thank Assistant Professor Inderman for his guidance during my master's degree, his diligence and ability to push and demand from himself and as well as from his students to the highest of standards holds a great impact on my ability to present my work here. Thank you.
Thanks a lot, Ohad. Thank you. So we have plenty of time for questions. Who wants to ask? Now's the time.
It appears that all is clear. So.
All right. Last chance for questions. All right. So thanks a lot, Ohad. And
Thank
that's
you,
it.
guys.
Thanks. Bye for now.
Thank you, guys.